Resume. All right, so we are going to go to your science notebook, and we're going to be talking today about water. Yay, water. Right, so solutions chemistry is only solutions chemistry because we are dissolving something in water. So we're talking about solutions that are happening in water. So let's just take a moment and talk about what exactly water is doing. And in addition, let's review how we have described solutions so far. So we are going to learn 2 more ways of describing solutions today. So let's review the 3 ways that we already know how to describe them. I'm going to draw sticks. I'm going to ask for your help. How can we describe solutions? You guys can't see what I'm doing. That's going to be helpful. Press escape.
Are we going over these together?
We will, but not right now. All right, Dejan, tell me one way you can describe a solution. By molarity. Excellent. I can describe the solution's concentration using molarity. And Claire, what's the equation to calculate molarity? Moles of solute in volume of solution. Thank you, Caleb. Where did that come from? Jaden. Oh my goodness. Yeah, I've got I think I should just start over. No, I have not had a Red Bull today.
That's probably why.
All right. Well, we'll figure it out. All right, Sierra. Sierra, what's another way I can describe a solution? I can do concentration before versus concentration after. That would be my MCVC equals MDVD. I can only make this statement because I am making an assumption about the solution. And let's see if Michaela can tell me what assumption am I making about these 2 solutions. What stays constant? Zach? The amount of moles. All right. The moles before is equal to the amount of moles after. All I am changing is the volume of the solution. That changes the concentration, but the amount of stuff doesn't change. It stays the same on both sides. So that's the theory, the solution theory that I'm basing this equation off of. There's one other way that we have described solutions. Jaden Hamilton, what is acids and bases? So we've compared acid versus base. And we say that an acid is a substance that has a hydrogen, and a base is a substance that donates hydroxides. And as a result of the H's and the OH's, Tyler, what molecule forms? HOH? H2O. You got it. HOH, which just is liquid water, which is the molecule. And we use the equation molarity of acid, volume of acid is equal to the molarity of base, volume of base, because we're looking for a specific point in this reaction. Josh, what point in the reaction are we trying to find? Equal amount of moles. There you go. In the lab, we are trying to determine equal moles of H and OH. And we call that neutralizing. When they're equal, it's neutral because all I have, if I have equal hydrogen and hydroxide, then all I have is water. Okay? Thumbs up if you're with me so far. All right. I can't go in lab and measure moles. I cannot go into lab and measure molarity directly. There isn't a molarity measuring device. There isn't a mole measuring device. In lab, I make most of my measurements by grabbing a balance and measuring mass. So this next way we can describe a solution is called mass percent. Okay? And in mass percent, it's super straightforward. Now we're talking about the mass of the solute divided by the mass of the solution. Note, not water, but the solution, and I multiply it by what number to turn it into a percent? And that will give me the mass percent. Well, it's like really straightforward. There isn't it. The only catch is if I give you the mass of water, you have to add solute and water together to get mass of solution. That's the only catch that there could be. So let's just do a problem and see what this could look like. Give me a thumbs up if you're ready for me to move the paper. All right, sweet. Take a second. All right. Good?
You did, and I was like,
Oh, sorry. Let's grab okay. All right. All right, so let's do a problem. Here we have formaldehyde. What mass of water, flip, turn, join me, I'm recording, I'm going to autofocus, and rotate.
what's going on here? This is gonna be trippy.
It's going to be okay.
Whoa.
This way.
That's not. It's gonna make an infinite number of images there.
It's going to be okay. Now it's just going to make an infinite number of this. It's not going to make it. All right. So we have an image of specimens that are in formaldehyde. What mass of water must be added to 425 grams of formaldehyde, which was used as a preservative, if we are trying to create a 40% by mass solution? This solution, which is also called formalin, is what we use to preserve biological specimens. So when I was in high school, it was straight up formaldehyde, but formaldehyde is carcinogenic and teratogenic, meaning it causes cancer, that's carcinogenic, and teratogenic means it causes,
Correct.
no,
Well, yeah. Mental illness.
close, it actually causes birth defects. So if it's carcinogenic, it means it can damage my DNA and make me sick. If it's teratogenic, it actually can damage your DNA to the point that you can pass it on to the next reproductive generation. Knowing that, scientists identified that we probably should come up with a plan B for preserving things. That's where formalin came in. So if you've ever done any lab investigations in anatomy and physiology or in biology class that worked with a preserved specimen like a starfish, crayfish, a fetal pig, it was in formalin. So let's calculate what the mass of water would have to be. So step one, list. All right, I have mass solute, mass water, percent mass. The mass of the solute is 425 grams. The mass of the water is a question mark, and the percent is 40%. I'm going to make my life easier and turn that into a real number by dividing by 100. Because I can work with the real number. Step one, write the equation in letter form. Percent mass equals mass of solute divided by mass of solution. Times 100, which I already divided by 100, so I'm dropping that part out. All right. Thumbs up if you're with me so far. Okay. All right. So Trevor, what are we attempting to find?
Mass of the water.
Where is the mass of water number located in this equation?
Solid.
In the solute. Oh, time out. Solute, you're adding. We are adding formalin.
Oh, of course, so it's a solution.
It's in the solution. But it's not just the mass of solution, because the mass of the solution is the mass of the solute plus the water.
So you have to do
0. We have to split it up. Yeah, we've got, this is one of the few times where I'm going to say, it's okay to use X. Cade, you're going to love this, right? It's okay to use X instead of a label. And it's also going to be okay to put numbers into the equation. It will make our life easier in this case. All right. So 0.4% equals mass of solute. We said that was 425 grams. Divided by mass of solution, which is going to be water plus 425 grams. Agreed? All right. We have to get X. We have to solve for X. So I have to get X to the top. So I'm going to cross multiply this statement up here. And I get 0.40 times X plus 425 equals 425. I don't know if you can really see this red marker. Sierra, what should I do next? I could distribute in, or I can simplify. We could distribute in, and then I would get 0.4 times X, and I get 0.4 times 425. Or I could just divide by. Agreed? It'll save us a step. We'll have to divide regardless, but it makes life a little bit easier. Okay, so I get X plus 425 equals, let's find that. What is it?
1,062.
Thank you. I was like, that doesn't sound right. 425 divided by 0.4, 1,062.5. I was like, we're going to get a negative number. Solve for X. So instead of adding, we are going to subtract. Minus 425 minus 425. X equals water equals. There we go. And how many significant figures did I give you?
3.
We'll assume that that was a decimal point. 3, 3, 3 here, so 638. Label? Grams. Grams. All right. They're not all this involved, but if you can do this, you can do anything I give you. Agreed? The biggest thing that I was looking for you to catch in this problem was that you were looking for water, and water is part of this bottom solution problem. That's the only way that you're going to get tricked by these. Look on the back of your periodic table in your solutions box. In the solutions box, you will see mass percent equals grams of solute divided by grams of solution times 100. All you need to know is when to use it. There are many solutions I purchase as a chemist that are sold by mass percent. I can look up acids and base solutions that are not sold by molarity, but instead sold by mass percent. It's just a more historic way of purchasing and selling things because everyone could grab a balance, measure out a mass, measure out a volume of solution, and mix them together. All right, mass percent. Sweet. That wasn't too bad. All right. Let's go back. Hello, board. All right. So we know how to do molarity. We can do concentration before and after. We can do acid base. We can calculate mass percent. If you were not aware of this, we are in chapter 15. You should be doing your independent reading, and that would be sections 1 and 2 are going to give you example problems that will help improve your understanding of these concepts. The textbook is really great at this because it gives you examples to do that show you how to do them. So this would be page 520 through section 2 ends It's really quite large, 540. It's not 20 pages of reading, it's 20 pages of content and example problems. Dejan.
How many more units do we have sitting now?
Two units. We're testing out of Unit 11 on Tuesday. Then we do Rate and Equilibrium, which is Unit 12. And we have Nuclear Chem, which is Unit 13.
We have our test.
And then we have our final. And there's a test for 11 and a test for 12. Alan.
When is the final review?
The final review?
Remember how we had a midterm review packet? Are you gonna have one of those?
Yeah, you will. I have to print it. Honest answer. Yes, you have one. I will print it for you. And then get that to you guys. So, yes, a second. I'll get that done tomorrow and have it ready for you guys at class. Okay. All right. Let's talk about water. Okay. So if I have a solution of water, a glass of water, up until now we've just been saying you have these little water molecules that are floating around, bumping, sliding, right, inside of this container. And today we're going to talk about refining this idea, because the water molecules are not just bumping and sliding and bumping and sliding and bumping and sliding. The water molecules actually are breaking apart. And they are forming hydrogen ions and hydroxide ions constantly. And as they bump and slide, one of the hydrogens gets stolen from a water molecule, making a hydrogen ion, and another one, and as a result it releases a hydroxide. And as the hydrogens and hydroxides collide together, they make water. And as they collide, they break apart, and as they collide, they come together. And so there is this constant. So there's an arrow going this way to say water is constantly dissociating, making ions, hydrogen and hydroxides. And at the exact same time, hydrogens and hydroxides are combining, arrow, this way, to form water. Yes.
That why it conducts.
Pure water still will not conduct. I know. Now, water that's tap water will, because it has ions in it that can carry charge. Right? You would think if water is auto-ionizing, it should conduct, and yet it doesn't because it's still a molecule, and the electrons are being shared covalently and not free to go around and transfer. I know. Strange. Right? So this concept, the fact that if you have a glass of water, you in fact do not have a glass of water. You have a glass that half of it is water and half of it is ions, and half of those ions are hydrogens and the other half are hydroxides. And they're colliding and breaking apart and colliding and breaking apart and colliding and breaking apart. And if your water is neutral, the volume or the concentration of hydrogens and the concentration of hydroxides are equal. Dejan.
So when we have tap water, since it has iron and stuff,
Yep.
when it's breaking apart, what does the iron do?
The iron can form iron hydroxide and precipitate out of solution. Or if we have more, and then that can change and make your water slightly acidic, and we can make it slightly basic. It can change. We can say your water is soft and your water is hard because of those ions that are in solution. Right? It'll also conduct because it has iron in it. It has ions that can carry charge. So this concept that water is constantly breaking apart into ions and reforming to make water is called auto-ionization. Auto-ionization. Auto meaning all on its own, forming of ions. So water is constantly breaking apart and forming together, and this concept is called auto-ionization of water. And if we measure, because we can measure these, we say that the concentration of hydrogen ions, I can measure it, and it is 1 times 10 to the negative 7th molar. And the concentration of hydroxides is also 1 times 10 to the negative 7th molar. And because we talk about concentration so much, scientists have decided let's come up with a shorthand symbol that indicates concentration. And so we write concentration as a bracket. So this bracket around my symbol means concentration. So as a scientist, I see a bracket around a symbol and I infer that it's measuring concentration. So the concentration of hydrogens is 1 times 10 to the negative 7th moles in 1 liter of water. The concentration of hydroxide is 1 times 10 to the negative 7th moles of hydroxides in 1 liter of water. Right? So just because it's negative 7th does not mean I don't have it. Negative 7 does not mean less than 0 or less than 1. It just means small amount in large volume, so that that ratio is less than 1. Thumbs up if you're with me so far. Okay. So negative 7 does not mean less than 0. It just means less than 1. And it's a ratio, so I still have stuff, and it's still very measurable. So if I compare these, if I say, how does the concentration of hydrogen compare to the concentration of hydroxide? I'll say, well, they make water, so the concentration of the water must be equal to the concentration of the hydrogens times the concentrations of the hydroxides. So if I put their concentrations in here, I get 1 times 10 to the minus 7th molar times 1 times 10 to the minus 7 molar. When I multiply powers of 10, what do I do to their exponents? So, Kale, what is the power of 10 for this? Negative 14. 1 times 10 to the negative 14th molar. Yeah. Gotcha. Okay. All right. So if the concentration of hydrogen is 1 times 10 to the negative 7, and the concentration of hydroxide is 1 times 10 to the negative 7, and they always equal water, then this must be a constant, because the amount of water can't change. Thumbs up if you're like, sure, I'll buy that. Okay. So this is a constant. And because it's a constant, we give it a little symbol, and we say this is the water constant. And why they chose a K, I don't know. But this is KW, which is the water ionization constant. And it is equal to 1 times 10 to the minus 14th molar. It's a measurement of how water breaks apart. So if I place, if we look at the back of your periodic table on our solutions list for solubility, we got things that were aqueous, which means if I put them into water, they always broke apart, they ionized. I have things that are PS, meaning partially soluble. If I put them in water, they kind of break up. Okay, that means that their KW, their ionization, or their ability to become an ion, would be less. Like this constant would be different because it doesn't completely break apart. So this is a measurement of how well a compound will break apart. Water breaks apart perfectly, and so we get this 1 times 10 to the negative 14. But that's not a constant for every substance. It changes for every single substance.
So the lower the water, the easier it is to break apart.
The lower the number, the less likely it is to break apart. Is that what you said? Yeah. Yeah. And they're determined experimentally, and there's a whole bunch of stuff that we do to come up with these values. All right. Okay, so KW, you cannot find this. You can't like theoretically find it. It could only be found experimentally. So it's all based off of lab data. And we look at concentrations, and then we measure concentrations. If I do this, what happens to concentration? If I do this, what happens to concentration? We graph it, and that's where K comes from. Okay? So K is experimentally found, and we need it because if we change this system, this hydrogen and hydroxide system, we're going to need to know what KW is because this is the constant that holds it all together. It's the glue that holds together the hydrogen hydroxide system. If I change hydrogens, if this goes up, this number has to go down to stay the same. If this goes up, this one goes down. Which, if we think about it, if I add hydroxide, I will use hydrogens to make water. So it's going to go down. If I add hydrogens, oh, they're going to use hydroxides to make water. So this is going to go down. Do you see how if I add something, I can shift the system? All right. So let's look at how we describe this. So the big idea is water's breaking apart. We are infinitely interested in how many hydrogens there are because how many hydrogens determines how acidic it is, or how many hydroxides determines how basic it is. And in my world, that determines whether or not the grass stains are going to come out of my son's baseball pants, or if it's going to eat his pants and turn them into acid wash jeans, right? So I am interested in describing how acidic is the solution, and conversely, how basic is the solution. So let's look at, in order to understand this, I have to take a little moment and grab your calculator and have a little discussion of a button on your calculator called the log function. Love it. Love it. This is like my favorite lesson.
So
Seriously, yeah. I like have a little geek out moment here over the power of math and why we care. All right. All right, here we go. Yeah. All right, turn and tell your table partner, or pause. On your notebook, write down which of those numbers is larger, A or B. So for problems, A or B, which one is larger? Just write down in your science notebook, A, B, A, B, A, B, whatever. All right, put your pencil down when you're done. Which number is larger? More stuff.
do you want us to say it or?
Negative numbers are so weird. Awkward. They're like imaginary numbers. All right, when you're done, pencil down. Ready? Okay, so we're going to do the everyone stand up, touch 3 desks, and talk to whoever you find at the, it's like you stand and walk and touch 3 desks on your little walk. Find someone, tell them your answers, come to a consensus, and then have a seat. All right, go. Touch 3 desks. 1, 2, 3. Find someone to talk to. You can make a team of 3. James is back here. Somebody? Okay. All right, which one's larger? 1, 2, 3.
Defense.
4. Excellent work.
Can I go?
Okay. 2. 3.
Can't you just like go
Thank you.
and be like, I have anxiety, can you switch me?
Still drama?
Yeah, kind of. It's different drama.
All right. Passive aggressive much? All right. Diane. Okay. 4 numbers. I'm going to grab my sticks. Let's go through and figure out which one is larger. one of these things is larger. It's like a Sesame Street game, but with math numbers. Mr. Cabela, number 1. A, 10 to the negative 2 is in fact a larger number than 10 to the negative 4. Number 2, Zach S. Good. Number 3. Here. Caitlin. 10 to the negative 6 is larger than 10 to the negative 8. And Ryan. 10 to the negative 7 is a larger number than 10 to the negative 14. Okay. When we describe solutions, we are working with molarities that give us negative exponents. So if I have a molarity of 3.2 times 10 to the negative 3rd molar versus 4.8 times 10 to the negative 1 molar, tell your table partner which one has more solute in it. Which one has more stuff in the solution?
I'm gonna take a guess and say the second one, but I have no certainty.
Why? So it's moles in solute. So the larger the top number, then the larger the molarity.
Oh,
That's right.
so then it's supposed to go 6 and B.
Yeah, so it's 10 to the negative 1.
I'm just wonderful.
B-A-A, right?
All right. Okay. So if I look at these two solutions with molarity, 3.2 times 10 to the negative 3rd molar and 4.8 times 10 to the negative 1 molar, I'm comparing moles per solution, mole of solute in solution. So if I have 10 moles and 10 moles, how does the volume here compare to here? Ben, thoughts? Which one has a larger volume number on the bottom? A or B?
Which one's larger volume?
Yeah, which one has a larger denominator?
I'm gonna go with A.
A, because it has a smaller number, right? The larger the bottom number is, the more negative your exponent will become. If this was 1,000 versus 10, 10 divided by 10 gives me
1.
10 divided by 1,000 gives me, the closer the number is to 1, the more stuff is in it. The more concentrated the solution will be. The more negative the exponent becomes, the larger the volume is, or the less stuff in the solution. Does that make sense? It's weird because we're talking with negative numbers, and scientists caught that. They're like, there has to be a simpler way to talk about solutions, because thinking constantly this negative, where you're like, oh, okay, it's like opposite day, right? The smaller the number means more things. So the smaller the integer number means more stuff in solution. The larger the number, like 9, 10, 11, 12, means less stuff in solution. So let's think of, so scientists were like, well, let's come up with a way to make this make more sense. And enter in the fact that math is a toolbox that we use as scientists. And so this isn't new. We use math all the time. So I'm going to show you a couple of examples of where we would also use this math tool. So here we have a population curve for human growth of population on the Earth, and it's showing us the population from approximately 1800 to about early 2000s. And if we were to want to have a conversation as scientists about this rate of change right here and this rate of change right here, it would be really hard to have a conversation because here the population is close to 1 billion people, and up here the population is between 6 and 7 billion people. So the difference in their numbers alone make it difficult to have a conversation about those two numbers and how they truly compare. Right? It's even more noticeable if we look at populations that start from single digits, like the growth of bacteria. So bacteria undergo asexual reproduction, and that is like the coolest thing. So here is a video of a microscope showing a cell undergoing asexual reproduction, binary fission, fission, cut in half, binary fission, cell reproduction of a bacteria. So, camera, microscope, observing this time frame. It was 1, then it was 2, then it was 4, then it was 8, then it was 16, then it was 32, then it was 64, and we are following a growth pattern that has a fancy name in math called exponential growth.
So will it just like from there?
Right, so here we are observing an example of where we see exponential growth. Exponential growth is a property of populations, whether the population is a population of bacteria. And you see how it's getting fuzzy? It's getting fuzzy because the bacteria are growing up. They're not just growing out, they're growing towards the lens of the microscope. So it's hard to talk about bacteria populations at time 1 and time 2 days, because here I have 4 bacteria. Here's 4. Sorry, at the end of 24 hours I have a billion. So it's difficult to talk about those if I want to look for patterns and trends. So scientists said, why don't we simplify this? How can we simplify this to talk about the patterns and trends in the data? So we've got this bacteria. I see that there are, I'm showing you the shapes of bacteria. There are 3 different shapes bacteria can be. They can be rods, they can be circles, or they can be spirals. Each of those has this fancy name. They can be cocci, that's a circle. They can be bacilli, that means it's a rod. Or they can also be spirilla, which means it's a spiral. So the name of the bacteria actually tells you its shape, Streptococcus. If you have strep, you're Streptococcus, those are circles, right? Meningitis. If we look at some of these, we can actually figure out bacillus, geobacillus, stromophil. So this comes thermophile. This loves a heat-growing environment, and it is a bacillus, which makes it a rod. Okay? So if we look at them, we see exponential growth. We've got to have a way of simplifying this, and it doesn't really matter that I have 1 bacteria. It just mattered that I had ones of bacteria. So if I described this and said I have ones of bacteria, and now I have tens of bacteria, and now I have hundreds of bacteria, and I change this from a number and instead a power of 10 scale. If I just say this is now power of 10, and when I had 1, I have a power of 10 of 0. And when I have ones, I have a power of 10 of 0. When I have tens, I have a power of 10 of 1. You following me? When I have 100, the power of 10 is 10 to the second. When I have 1,000, the power of 10 is 10 to the third. When I have 10,000, power of 10 is. So if I just talk about the power of 10, I can transform this graph and make it go from 1, 2, 3, 4, 5, 6, and it becomes a straight line. That's really easy to talk about straight line. Y equals mx plus b. Simple. So scientists are like, let's stop talking about the actual concentration and let's just talk about the power of 10. Because it doesn't matter that I had 1,234, it just mattered that I had 1,000. So as scientists describing solutions that have tiny, tiny, tiny concentrations, they said, let's just try and simplify this, and rather than saying you have 2.3 times 10 to the negative 8th, let's just say that you have the negative 8th power. And the negatives are really awkward. So can we just drop the negative sign and everybody agree we just call this a positive scale because it's just a scale? All right, because that's really awkward to have a -8. So let's just put a negative sign in the beginning of the equation so that all the numbers we get are positive, because that just makes our brain a little bit happier. And now we're not talking about powers of 10, we just talk about a number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. And what scale is it that they created?
The metric.
No.
Oh.
Describing solutions, acids and bases, from 1 to 14. The pH scale. All right, grab your calculator.
Second try, got it.
All right, find your log button. Your calculators are set up to make your life easier if you choose to use them. The log function in math describes the power of 10. So on my calculator, I find my log function. And for most of you, you're going to push the log button and then type in 1,000 and hit enter. Log 1,000, enter. And the number is 3. Because the log function tells me the power of 10. And 1,000 is 10 to the third. Oh, look at that. Okay? Now try log of 2,000. It's 3 in calculator junk because it's more than just 10 to the third, right? So that makes sense that it's 3 with a remainder, 3.3 blah, 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 blah. But what's the power of 10? 3. Okay, right. Okay, how about 0.001? Log of 0.001. -3. Okay, so log means power of 10. What does log mean, everybody?
Power of 10.
And whenever I want to show that I've used the log function, I put a lowercase p in front of whatever number I've used. So p of H means the power of 10 of hydrogen. I have used the log function to get the concentration of hydrogen, pOH. Oh, power of 10 of hydroxides. I can do the P of cars, the power of 10 of the population of cars. I can do the population of people. I can take the log function of the population of Kearney High School. Right? If I said, what is the P of KHS? I'd be saying, what is the log of the population? And it'd be the log of 1,400 students, which is approximately 3. What's the power of 10? So it's going to be 3 with the remainder, but that's essentially what we're saying. Okay? Anyone can regurgitate the equation. The equation's on the back of your paper on your solutions. Okay? If it's P, it means we're using the log function. Log of whatever came after. Log of hydrogen, log of hydroxide. If you don't know hydrogen, you can find hydrogen if you know hydroxide in KW. If you don't know hydroxide, you can find hydroxide if you know hydrogen in KW. Like, we can solve for all kinds of fun stuff and manipulate these equations lots of ways. Thumbs up if you're with me so far. All right, in your science note updation, question. Excellent question. We will put the concentration number, whatever they give us in the problem, to figure it out. Okay? The molarity, exactly. So if you found the molarity of your acid in lab yesterday, and I said, what's the pH of your acid? You would do negative log of molarity. And so you guys had a molarity from your acids lab of 0.18 molar. So if I said, what's the pH? I go negative log of this. Negative log of 0.18. Negative log because this power is 1.8 times 10 to the minus 1. And if I put the negative here, it makes my pH scale a positive number. So then it would give me 0.745. Yeah? All right. Okay. Okay, so it's difficult to describe solutions using powers of 10 and negative numbers, which is why we describe them using pH and pOH. Both of these equations are in your back of your periodic table. And we have a worksheet in your packet that says pH, pOH worksheet. Let's go there now. Yes, we are. We will talk about inverse log tomorrow. Your calculator is set up to help you. The opposite of addition is
subtraction.
And they are side by side. The opposite of multiplication is
Division.
And they are side by side. The opposite of log is inverse log, which is 10 to the power, which on your calculator is second log. Log to the negative 1, which is not log to the negative 1. It's what is log? Log is telling me power of 10. So the opposite of power of 10 is 10 to a power.
Okay.
Great. The pH scale says solutions with a pH of 0 to 7 are classified as acidic. This should not be new. This is like 6th grade, right? Solutions from a 7 to a 14 are basic. Why? Because this is a concentration of hydrogens equal to 10 to the negative 1. And that is a bigger number than 10 to the negative 14. Agreed? Which is why we talked about negative numbers. It seems backwards, but remember when we did that pH equation, we said negative log of hydrogen. Okay. All right, let's go to your worksheet. pH, pOH, solution. I don't know what I did with mine. Maybe it didn't pull it out yet. No, we won't work with natural log. We'll just work with log and inverse log. Here it is. All right. Thank you for your patience. Okay. Here we are. Define a solution. Describe solutions using vocabulary. We've done this. List the factors. We haven't talked about that. Calculate mass percent and molarity. Agreed. Read about what a standard solution is. Calculate concentration of a dilution. We've done this. Calculate acid-base titration using indicators. We have not yet talked about 7. We have described how water ionizes and the ionization constant of water, and we can calculate HOH, pH, and pOH, which means we are almost done with this unit. And if you haven't done any of the reading, now would be a fantastic time to start. Deja. There might be one in the folder over there against the wall. Check it out. All right, pH, pOH. pH, pOH. Okay, on the top of your paper, 1 to 7 to 14. A pH of 1 to 7 is called acidic. A blurry mess. It's coming. Come on. 7 to 14. Guys, pause your conversations, please. 1 to 7 is acidic. 7 to 14 is basic. Ben, pause, please. Okay. Let's look at number 2. A solution with a hydroxide concentration of 3.4 times 10 to the negative 12, would it be acidic, basic, or neutral? Well, the first thing that I have to acknowledge is that acidic, basic, or neutral is based on the pH scale, not the pOH scale. So in order to answer this question, I have to figure out what's the concentration of hydroxides. And I know Kw equals hydrogens times hydroxides. So if I want to solve for hydrogen, then I divide hydroxide over to the opposite side. So Kw divided by hydroxide concentration will give me hydrogens. Kw is that ionization constant of water. Trevor, what was that number?
Water.
Yep, ionization constant of water.
Negative 14.
-14. Good. And then I have hydroxide, which it tells me is 3.4 times 10 to the negative 2. Grab my calculator. 1 EE negative 14 divided by 3.4 EE negative 2. Concentration of hydrogens is 2.9 times 10 to the negative 13. Ten to the negative 13. The pH value of this is going to be what, Bailey? Roughly. The power of 10 that we're looking at here is it's just 13, right? So where's that going to fall on this scale? Acid base.
Good base.
It's going to be a base. See, pH equals negative log of H, negative log of 2.9 times 10 to the negative 13, negative log of 2.9 EE negative 13 is 12.5. It is basic.
What
You
is
go
the
through that
answer?
one more time.
Yeah.
You just like is that your what's your answer exactly?
Basic.
Just basic?
The answer is this solution acid, basic, or neutral? The
Why
answer
do you
is
have to do the 2.9 part, like the negative log 2.9 times
If-
13? You already wrote that down, so
I wrote it down to prove that I was right. pH equals 12.5. I looked at this number and I observed that the pH is the power of 10. I see that the power of 10 of hydrogens is 13, which on this scale tells me it's going to be basic. But if that's not a skill that you're at yet, then you would just do the pH equation. And when I plugged it into the pH equation, I'd say negative log of concentration is 12.5. I would go to the scale and be like, hey, look, over 7. This is basic. Should we do another one?
yeah.
Calculate the pH and the pOH of a 0.1 molar solution. All right. Okay. All right. So I know Kw, H plus, and OH minus. Kw is 1 times 10 to the minus 14. Always, forever. That will not change. Calculate the pH and the pOH of a 0.01 molar solution. So what's the concentration of hydrogens? 0.01. All right. It wants pH and it wants pOH. The equation for pH equals negative log of H plus. Do I have enough information to solve that? Yeah, okay, so let's do it. pH equals negative log of 0.01 molar. Pretty sure that that's a 2. This is 1 times 10 to the minus 2. Log says, what's the power of 10? The power of 10 is 2, negative 2, and then there's a negative, which makes it a positive. I take it, plug it in my calculator, negative log of 0.01, enter. And it tells me 2. Negative log of 0.01 is 2. pH is 2. All right. Kw is always 1 times 10 to the negative 14. Okay? There's also some really easy things that I can do here too. pH plus pOH will always always equal 14. Because hydrogen was 10 to the negative 7, and hydroxide was 10 to the negative 7. And if I took the log of that plus the log of that, I'm going to get 14.
So it's a base.
Hmm?
So it's a base. That's incorrect.
This is acid.
Oh shoot.
Equals 2.
Wait, why did you say the pOH? Is that for the next problem?
Right. So calculate pH. I could calculate pH because I have H. Then it says calculate pOH. Okay, well, pH plus pOH equal 14. So pOH is 14 minus pH. 14 minus 2 is 12.
So
That does not make it a base though, because acid base is determined using the pH scale. The words acid and base only apply to the pH scale,
or not pOH.
not the pOH scale.
Do you want us to write?
on the pOH scale is an acid.
Yeah.
Do you want us to write that acidic?
Yeah, you should still understand that that's acidic. Yeah, the pOH scale would say that low numbers are high concentrations of OHs, which would make it acidic. High numbers are low concentrations of OHs, or it's backwards. Low numbers make it basic, high numbers make it acidic. That's why I just say that acid-base words only apply to pH scale. That's the land that we live in. We don't measure hydroxide concentration. We live in an acidic world. We measure hydrogen concentration. Your stomach is acid, not base. So everything we do always is interested in the
What about your
acidity of it.
skin? What about your skin?
I love that. All right.
It's a base for everything else.
Should we do another one?
Yes, please.
Calculate the pH and pOH of a 0.34 molar solution of hydroxide. Okay, well they gave me hydroxide this time. So concentration of hydroxide equals 0.34 molar. I have to find pH and pOH. Which one should I find first? pOH. Sure, because that's what they gave me. So that'll make my life easier. pOH equals negative log of hydroxide equals negative log of 0.34 molar. I don't know if that is off the top of my head. Maybe like 1 something. Okay, everyone grab your calculator and make sure that you can get this number on your calculator. Log of number, or depending on how many you got.
Show me again.
Here's just log of number, log of number. You push the log button and then the number. And you need to put in negative log 24. And you get
0.46.
Yep. 4685210 blah 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 blah. Sig figs? 2. Sig figs an answer? 2. Answer is 0.47. Is there a label? No. It's on a scale. There's no label. It's just a number. It's just a system, it's a scale. Okay. So this is pOH. What else do we have to find? pH. So we can just do pH plus pOH equals
14.
14. So we'll just subtract it. pH plus pOH equals 14, which means pH equals 14 minus pOH.
13.
How many sig figs?
2.
2. Final answer.
14.
And you're like, what? That doesn't work. But it does.
So it's base.
It is a
Very
base.
basic.
A very strong base. Because it's as far over to the right as we can possibly get. Very basic.
I wonder if it's
Okay.
acid.
Your homework. It's not nitric acid. That'd be very acidic. Alright, your homework is the rest of the worksheet. Tomorrow we are doing a lab where we're calculating the molarity and the pH of aspirin. This is what I want to see. I want to see information you're given. I want to see the equation in variable form. Do you need, so I want to see this. I want to see this. And then you can give me the answer. Okay? And you can give me this. And then you can give me the answer. If you don't feel like doing the nitty-gritty stuff in the middle, because you can do that on your calculator, fair enough. The more you give me, the more points I can award you if you make a little calculator error versus not.
Man,
I know, the wind picked up this afternoon. Not buying it, but fair enough. I appreciate the change.
16 people have seen it, but no one has responded.
If you know the subtracted from 14 and then the pH, and then if you need to find this next, I forgot to do the inverse log to go backwards. The other way to find it would be hydrogen times hydroxide equals 10 to the negative 14. Here's me. I wasn't going to show this to you until tomorrow, but I think that some of you are kind of figuring it out. Alright, on your calculator, let's say that, is it this one, Kate?
Yeah.
Alright, let's look at this. Calculate pH of a solution of, no, this is 6.
Yeah.
Find the hydrogen concentration of this. Okay, so there's one way I can do it. Kw equals 10 to the negative 14 equals hydrogens times hydroxides. Option 1. Agree?
Yeah.
That's probably the easiest because they don't ask me for pH and pOH. But let's say that I'm given, like in number 7, they give me pOH. And they ask me for the hydrogen or the hydroxide concentration. Okay, so this is where we're using pOH equals negative log.
This is 7 that you're writing down?
This is 7.
Oh.
Okay, so I'm not doing 5, I'm looking at 7. Ben.
Oh, I just needed to ask you if I did this right.
Okay, I'll come look in a second. In number 7, they're asking us to work backwards. They want to know this if they tell us this. And math tells me, oh, to solve for the unknown, I divide whatever this is to the opposite side. Right? And in geometry, we would say, oh, I divided cosine to the opposite side, so it becomes inverse cosine, or cosine minus 1, or sine minus 1, or tan minus 1. Give me a thumbs up if you know what I'm talking about. Right? Or it goes from 2 to being 1 over 2, inverse 2, okay? If I bring negative log over here, I do inverse log. Inverse log is the second log button on your calculator. The function will look like 10 to the x. This is inverse log, because log is power of 10, so the opposite of telling me the power of 10 would be 10 to the power. In my calculator, if I'm solving for this, then I would want to know OH minus equals inverse log of minus pOH.
Why did you put the minus on the
Because there's a minus sign right here that I can't forget about. inverse log of minus, and they told me the pOH was 7.8. Have to have a negative in there. Inverse log, so second log minus 7.8. And we get a concentration of scientific notation. Times 10 to the negative 8.
Well, your calculator isn't in scientific form.
1.6266.
Gets
Mode. Psi.
Gets put the 10 negative.
Absolutely. Because that's the difference between having $1 and having 1/100 of a penny. Go to your mode. Only if it doesn't tell you.
I did.
And then pOH would be 14 minus that.
What is
14 minus pH equals. Bailey, what you thinking? What makes sense?
Well, I mean, 7 makes sense, but like 6, I don't know, like is KW, so is it 1 times 10?
1 times 10 is negative 14. Don't be scared if you just see 10 as a negative 14.
Whoa, that is some naughty language. Science. It's not.
You know what this is? This is scientific.
And so, KW
I can imagine very many people go to that student.
Exactly.
Okay, when people find the use a lot like and sort of yeah. And then
So like not a lot of people that look at
We need to define as
unless they work at like a unit store.
So negative pOH.
On both
pOH
sides,
equals
that
inverse
she's
log.
asked for 2 extra.
Inverse log is just
Inverse
second log. Log negative.
The first time, I was like,
We just did. We just did.
Inverse log is just like multiply. I was like, oh crap.
I'll be charged for 2.
Yes. It's just a different
Inverse
concept
lines.
that you use every day.
Give it a day or two. Those one ones that actually.
And I'm big about understanding what you're doing.
You didn't start on. Wait, are you in? Algebra 2. Oh, you're not. Algebra 2. I know. It's like I feel like really good at
Okay, my ultimate goal is I'm going to get to level
You're doing really good.
2.
Okay, I could take those.
Like, and then I'm gonna do stop.
If you really,
And if someone goes to what, like, go over it, I'm gonna be
And then you have to get the inverse log negative.
I feel bad about myself.
I was like,
I can't. I would show you.
You know what I mean, though? Just people that I would
I like to answer this.
There's some crazy math words I had the privilege of figuring out the fancy math before, and then I was like, that was good. Alright. Okay, homework.